All right, so hello and welcome everyone to the fourth week of interactive live sessions for the course on fundamentals of convective heat transfer. It's being offered by NPTEL. Uh, we are being taught by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras, and I'll be the TA for this course. Like every other week, we shall be solving some problems together. So without any further ado, let's dive in. We will take a look at the first question of today's session, which is asking us, it's a true or false type of question. So there's a statement given and it's asking us to select whether it's true or false. The question is that in integral formulation, the conservation laws are satisfied in an average sense. Is that statement true or false? Read the question carefully, and once you have figured out the solution, you can unmute and answer, or you can type in the chat box as well. In integral formulation, as opposed to the other kind of formulation, which is differential formulation, the conservation laws are satisfied in an average sense. Is that statement true or is it false? So what happens is there are two different kinds of formulation. One is an integral approach versus a differential approach. So in differential approach, what is done is that we take a control volume which is infinitesimally small. So it's dx, dy, the all the dimensions are infinitesimally small. Now in integral approach, what we do is we have a finite sized control volume. Now it could be in one dimension or more than one dimension. So usually in boundary layer analysis, what is usually done is that we take a control volume which is infinitesimally small in the x direction. So this is still dx, but in the y direction we have a finite size of, you know, in this case the boundary layer thickness delta. So it could be the other way around also. We can also, have a much larger control volume with, let's say this x dimension being L and the y dimension being delta. In that case, also, if we solve for the conservation laws in this sense, that is also known as an integral formulation. Okay, so we have one answer in favor of statement A, that is true. Let's have a look at the solution. It is indeed true. So we discussed this in the previous slide here. So this is the case of an differential formulation, and these are examples of integral formulation. And in this case, the conservation laws, they are satisfied in both the cases because those laws are, the equations which we solve comes from those conservation laws themselves. But if we solve them for a differential through a differential formulation, what we get are known as exact solutions. In that case, there are no approximations involved. We know we solve for the exact fields of all the unknown variables that we are solving for. But in an integral approach, we don't get the distribution of different physical quantities, but rather we can get flux through, let's say, this whole surface. We don't know the distribution throughout this surface, but we know what is the total amount that goes in, goes out. That sort of an idea we can get through the integral approach. So in that way, the conservation laws, they are satisfied in an average sense or in a more overall sense, not in the exact sense. Okay. So any questions on this? Okay. So let's keep moving on. We'll move on to question number 2, which is asking us that advantages of integral formulation of laminar boundary layers is or are then Four statements are given. Statement A is simpler than exact solution. Statement 2 is reasonably low errors. And statement 3 is more flexible than exact solutions. Or is it option D, all of these? Okay, we have a response in favor of option D, that is all of these. Let's take a look at the solution. It is indeed all of these. So first of all, because we are solving for a lesser number of variables and we are not looking at distributions, the solution process becomes much more simpler than exact solution of the entire thing. And we saw in the lectures that even after assuming uh, an integral approach and assuming that distributions are some polynomial function, so in that case the velocity and temperature profiles, if we assume that they follow a polynomial function, e- even with such gross simplifications, we get reasonably low errors within 10% or so. So the errors are also lower. And given this trade-off that we are getting a simple solution, uh, but we are getting more errors, these are not as good as exact solution. But anyway, that amount of error is not too much. If I can live with it, then fine. And option C is that it's more flexible than exact solutions. This is also true. So since we're making those simplifying assumptions, we can make different kinds of assumptions, and that way we can customize our approach to different uh, axioms or something that we can customize it to different assumptions that we make. So what I mean by that is, let's take an example. So if I'm assuming it's a polynomial function, some polynomial function, then I have the flexibility to decide whether it's a second order, third order, fourth order, or nth order polynomial. I can decide that. The errors that I'll get and the solution accuracy which I'll get will depend on that, but I have that flexibility to choose from to begin with. So this is another advantage, this added flexibility which it offers. So since all these three statements are correct, the option D would be the correct solution to this, which is all of these. Any questions on this? Okay. So moving on, we have to solve some certain things numerically now. So it's telling us that assuming linear velocity profile. So here our flexibility comes into the picture. I assume that my velocity profile is linear, first order polynomial, or rather I can say zeroth order polynomial. No, not zeroth order, first order polynomial. And then we're using approximate momentum integral method, which we learned in the lectures of week 4. And it's an integral approach, as we have been discussing. So you have to find the value of expression, this thing, CF into under root REX, where CF is the coefficient of friction and REX is the Reynolds number at length x with respect to x. And we have a hint given that for linear velocity profile, we can find out that this uh, the boundary layer thickness delta over x is equal to some 3.464 over under root rex. We have to use these information. So the given informations are this and this. So using that information, we have to find out the value of CF into under root rex. So the way to do this would be to first of all start off with finding or associating CF with the velocity profile. So uh, what is CF? By definition, it is the shear stress at the wall over half rho u infinity squared. And the shear stress at wall we know can be found out by using this formula, mu into dou u dou y. This is Newton's law of viscosity at y equal to 0. So we know the expression for u. So from here I can tell that u is equal to u infinity into y over delta. So u and delta, these are constants. So it's mu infinity by delta. And if I differentiate with y once, I'll get 1. So that's the uh, tau wall. So let's now start putting in values. Okay, so I'll need the delta as well, which I can get from this expression. So delta is equal to, so delta is equal to 3.464 into x over under root rex. Okay, so we have a solution which is 0.577. Let's see if we can go there. All right, so this is delta. Now I'll start putting in the numbers. So I have, 2 into tau w. So I have 2, and tau w I can write as mu into u infinity. I have 1 over delta outside. I'll keep that for now. So I'll just tell this 1 over delta I have here, and I have rho into u infinity squared. And now I'll replace this delta with this value. So let's do that. So that is 3.464 into x and over rex. So let's expand out rex as well. So that is nothing but u infinity into x over nu. Nu also I'll break it down, or let's keep it as nu. And I know that, you know, the mu over rho, that gives me nu. So I have one nu in the numerator, right? And this u infinity cancels out. So, okay, so let's look at this. So the numbers which I have is 2 over 3.464, and I have nu over here. Sorry, I have a nu over here. I have a u infinity, I have a x, and I have this thing, u infinity into x over nu. So if you realize, this is Rex and this is also 1 over Rex. So, and this number 2 by 3.464, I guess that's what gives us this thing, 0.577. And this is basically 1 over Rex into root Rex. So that should give me 1 over root Rex. And this is what CF is equal to. So with just one more step, I'll write CF into under root Rex. That should be equal to 0.577. Any questions on this? Cool. So let's move along. We'll move on to question number 4 now, which is asking us that for a laminar boundary layer flow over a flat plate with air at 20 degrees Celsius and 1 atmospheric pressure, which basically means Prandtl number equal to this, 0.709. The thermal boundary layer thickness delta T is approximately 21% larger than the velocity boundary layer thickness delta. So this information is given. Now the question is asking us to determine the ratio delta over delta T if the fluid is ethylene alcohol with a Prandtl number of 211 under the same flow conditions. Same flow conditions meaning the same, Reynolds number and associated things. So if the Reynolds number is the same, we can say that the uh, flow over it is the same, and as a result, the heat transport would also be similar. So in that case, what would be the uh, delta over delta T? So the way to do this is, first of all, we know that delta over delta T is equal to Prandtl number to the power m, where this value of m depends on the flow condition. So we have learned that M is equal to one third for laminar or half for turbulent and so on. So it really depends on the flow conditions. So the flow conditions which are not explicitly given, but we have to find out. So what is given is that in the first condition, delta T is 21% larger. So if I say that, delta is 1, then my delta T is 21% larger. So 1 over 21. This is the first case. And equal to Prandtl number, which is the value of Prandtl number is also given. So that is 709 to the power m. So from here we have to find out the value of m. What we do is we can simply take log on both sides. So that will give us m log of 0.709 should be equal to log of 1 by 1.21. And this should give us the value of m. So just quickly calculate. If you can help me with the numbers, that would be great. So let's find out this first thing. The log of 1 over 1.21, it's 0.55. No, I'm getting some negative number. Getting minus 0.0823 over here. And 0.709, sorry, 0.709, that is minus 0.1494. Okay, so now 0.0823 divided by 0.1494. Yeah, that's point. Okay, you are telling the final value of m. Yeah, that's correct. 0.55 is the value of m. Now we have to use this value of m to find out the new delta y delta t, which is for the second case of ethylene alcohol or ethanol. So in this case, I have Prandtl number. We'll use the same formula, Prandtl number power m. I have, okay, so they're telling me the answer is 18.98. We'll take a look at that. So I have 211 to the power 0.55. So if it was zero point 0.5, it would be square root. So roughly square root of 200. Yeah, so 18 makes sense. I'll do the calculation once. I have 211 to the power 0.55. Yeah, 18.98. Perfect. That's the answer. Any questions on this? So what does this mean physically? So physically, we got that, the thermal boundary layer was 21% larger in case of this thing for air. Now, in case of ethanol, it would be the other way around. Delta would be much, much larger, and in fact, close to 20 times larger than the thermal boundary layer. So the thermal boundary layer will be very thin in this case, and the uh, hydrodynamic boundary layer would be much, much larger. And this is primarily because of the length of the magnitude of these Prandtl numbers. So if Prandtl number is 200 as compared to zero point 0.7, that means your viscosity is much, much larger than the thermal diffusivity. So the thermal diffusivity is very small as compared to the viscosity. So the viscous boundary layer will be much larger than the thermal boundary layer. Okay. Any questions on this? If not, we'll move along. We'll move on to question number 5 now. Okay, so this is again a numerical type question. It's telling us that air at a temperature T infinity flows over a flat plate with a free stream velocity of U infinity. Now, given the plate is maintained at a constant temperature of TW, and the velocity and temperature at any location are given by these formulas. So I have the sinusoidal velocity profile and a second order temperature profile. In that case, these are normal uh, notations. So given that, and all these numbers are given, U infinity is what, this relationship between delta and del T is given, TW is given, T infinity is given, and all the material properties are also given, and as well as the hydrodynamic boundary layer is also given. Given all this, you need to find the shear stress at the plate surface. Which one should it be? There are four options given below. One is 200 by pi, 400 by pi, pi by 200, or pi by 400. So try to solve this correctly, and once you have figured out the correct solution, you can unmute and answer, or you can type in the chat box. Okay, so you have a response C, that is pi by 200. Let's take a look at the solution. It is in fact pi by 200. Good. So how do we go there? So basically, finding the shear stress should not be much of a problem because it's just tau w equal to mu into dou u dou y at y equal to 0. And we already know what u is. So I have mu into u infinity. And then we need to take the derivative of this thing, sine into pi y by 2 delta with respect to y. So first of all, pi by 2 delta would come out, and then differentiation of sine would be cos pi y by 2 delta. And since we are evaluating this at y equal to 0, so the argument of cosine becomes 0. So this goes to 1, and we are left with mu into u infinity into pi over 2 delta. And if we now plug in values, so mu I know to be 2.5 into 10 power minus 5. Okay, so there was a typo here. It's not 10 minus 5, it's 10 power minus 5. Yeah, I have that. Then u infinity is 10. We have pi over 2 into delta. So over 2 into delta is 0.025, right? Okay, so I can simply remove this one and multiply by 10 minus 1. I can remove this and multiply by 10 minus 3. Then 25 cancels out. And what I'm left with is pi divided by this one I'll take down. So this is 10 power 5 minus 1 plus 1. Okay, so these two again cancel out. So minus 1 plus 1 I won't do. So 10 power 5 comes here, minus 3, and I had a 2 in front. So this is 100 into 2. So yeah, pi by 200. That's the correct solution. Any questions on this? Okay, so let's move on. We'll move on to question number six now. Again, a true or false type of question, which is asking us that the Leibniz integral rule gives us a formula for differentiation of a definite integral whose limits are functions of the differential variables. Is that statement true or is that false? Okay, so we have a quick response in favor of true, and it is indeed true. So we use this Leibniz integral during the derivation of momentum integral equation. What this rule basically tells us is that if I have a definite integral like this, which goes from, let's say, some a to b, a is a function of x and b is also a function of x, and I have something like this, dou f dou x into dy. Uh, and y is a function of this x, right? So, wait, that's not the correct way of doing this. So this basically lets us convert this into, okay, I'll remove the partial derivative. I'll just say df dx. In that case, I can take the differential operator out, given these are all linear operators. See, if it was not a definite integral, then flipping the sign of differential and integral is not an issue. So if I have something like this, I have df dx into dy, let's say. In that case, I can, and if this was a indefinite integral, then I can easily convert it into ddx of f dy and live with it. That is a very easy thing to do. Now the problem here comes if there are limits uh, to the integration. If it is a definite integral, then we have to invoke this Leibniz integral rule, which tells us that if I take out this ddx and I do the same integration of ax to bx over f dy, then I need to there has to be some addition to it, which is basically uh, b prime of x into f at that location minus a prime x into f at that location. So at b and at a. I hope I'm doing this correctly. I'll just check once. Yeah, that's the correct way. Well, no, it's the opposite. Okay, so it's the other way around. Uh, so if I take a derivative of this thing, ax to bx into f dy, then I can put this differential inside. This will be a not a partial, but rather a proper differential plus this thing. Yeah, I just wrote it a bit wrongly. This is the correct way. Okay. Any questions on this? So let's move along. We'll move on to question number seven, which is again a numerical type question, which is telling us that I have a flat plate which is 5 centimeters thick has a thermal conductivity of 1 watt per meter Kelvin. The convective heat transfer coefficient on its two flat surfaces, sorry, on its two surfaces are 10 and 20 watt per meter square Kelvin respectively. What is the overall heat transfer coefficient for such a flat plate? So we have a numerical type question here, which is telling us. So the physics of the problem is like this. I have a flat plate like this. It is some thickness T, which is the value is given 5 centimeters, and it has a thermal conductivity K, which is also given 1 watt per meter Kelvin. Then I have heat transfer coefficients or convective heat transfer coefficients on both sides. Let's call them H1 on this side and H2 on this side. These values are also given. H1 is 10 and H2 is 20 watt per meter square Kelvin. So in such a scenario, what is the overall heat transfer coefficient? So given I want to transfer heat from this end, from let's say point A to some point B over here. There are, different fluids in between where convection takes place. So from this point A to B, what is the overall heat transfer coefficient? So if you look at this in a different way, this is exactly like how you solve for resistances in, uh, analogous to an electrical circuit. So I have one resistance here, which is this fluid on top of this flat plate. Then I have another resistance, which is like the conductive resistance through the flat plate. And then there is another fluid which acts as another resistance. So there are three resistances which are connected in series like this from point A to B. We'll call this resistances R1, R2, and R3, let's say. So in that case, the question becomes what is the overall or the equivalent resistance? So in case of heat transfer, what is usually done is uh, you know, since we're drawing analogy with electrical circuits, so I'll start with Ohm's law, which tells us that V equal to IR, or I can write it this way, I is equal to 1 by R into V, where 1 by R is the conductivity, conductance rather, 1 over resistance into the voltage difference. So analogous to that, the analogous to current in heat transfer is the heat flux, which is Q dot double prime, and that is equal to or just Q dot, right? And 1 over R, the conductance, that is the heat transfer coefficient actually. Heat transfer coefficient into area. So if I have flux, then it's a different issue. So I'll just maintain double prime here. This is basically Q dot per unit area. That is equal to H into, so H is 1 over R, and the analog to voltage difference is the temperature difference, basically. So T minus T infinity. I hope you see the analogy here. So current is like heat flux. The 1 over resistance or conductance is like the convective heat transfer coefficient, and voltage is similar to the temperature difference. So with that idea, what can we say about these R1, R2, and R3? So this is for convection. Similarly, for conduction also, we have an equation like this, where this is K into dou T dou Y. We can integrate dou T and dou Y. So in a more discrete sense, this again becomes K into delta T over some L, and K over L is equal to that conductance into the delta T again, which is the voltage difference. So this is for convection and this is for conduction. Now help me with it. So coming back to our problem, what should be R1? Okay, we have a response in favor of option A. Okay, we'll go to the solution later. Let's do this first. So the resistance, the first resistance, what should it be equal to? This one. Just look at the analogy here and tell me what should be the first resistance? This one. Over here, whatever fluid is there that is offering some resistance, what is that equal to? Hello. 1 by 10, correct. Then similarly, R3 should be 1 by 20, right? They are both similar. What about R2? What should R2 be? 5 by 1, correct. So basically it's K by L. I'll remove this thickness T and call it just L. So K over L is, and these are 1 by H, by the way. 1 by H1, and in this case, 1 by H2. And this is K by L, and that is equal to, K is 1, sorry, not, what did you write? 5 by 1. Well, no, it should be, so the K is, K by L is the resistance, right? No, sorry, yeah, you're correct. This should be L by K, and L is 5 centimeters, so 0.05 by K, which is 1, right? So the overall resistance or the equivalent resistance, that is equal to 1 by 10, which is zero point 0.1 plus 0.05 plus 1 by 20, which is zero point 0.05 again, right? 10 and 20, 1 by 20. Yeah, so this boils down to zero point 0.2, and this is resistance. So overall heat transfer coefficient, let's say U, where you know Q is equal to U into delta T, Q dot double prime. Sorry, Q dot. Yeah. So that U is equal to 1 by R, and that is 1 by zero point 0.2, and that should be 5. So yeah, option A should be the correct answer. And it is indeed the correct answer. Any questions on this? Okay, so we'll keep moving. Move on to question number 8 now. This is something similar to what we discussed in the previous session last week. So the question is that for laminar boundary layer flow over a flat plate with uniform heat flux condition, this is important. With uniform heat flux condition, that is the heat flux everywhere is constant. The temperature at the wall is given by this. So T wall is actually T infinity plus some constant C into x power m, where m is again a constant. So you have to select the correct value of m. What should be the correct value of m so that I can have a uniform heat flux condition? Is it half? Is it minus half? Is it 1 or is it 0? There are four options. Okay, so we have a response in favor of half. Let's take a look at the solution. It is actually half. Yeah. So the way to solve this is a bit involved. So what you need is the uh, the expression for q as it varies with x. So I'll try to pull that up. Give me a second. Or we can do it using the Nusselt number definition as well. Maybe. Let's see. So if we try to solve this using the Nusselt number definition, so the Nusselt number at x is given by some constant c into Reynolds number to the power half into Prandtl number power one third. Correct. So and Nusselt number is basically hx over k. So using this, I can find out that h is equal to some another constant. I would say so some c1. If this is c1, this is let's say c2. And RE power half, let's break it down. So Prandtl number also I'm taking as the part of constant K and uh, okay, let's just call this C1 K Prandtl number, and I have REX power half minus or RX power half by X. So now I need to find, so then Q is equal to T wall minus T infinity into H, right? This heat flux. So this thing is equal to some C into x power m, which we got from here. And the H is equal to this, which is again some more constants. Then Reynolds number, let's break it down. So Reynolds number, if we break it down, it becomes, uh, sorry, it becomes U infinity into x over nu power half. I have 1x here. Yeah, this should be okay. So I'll just club all the constants together into some C2 and just write this as x power half minus 1. So half from here, minus 1 from here, and plus m from here. So this is, so it boils down to Q double prime. The flux is equal to some constant into x power m minus half. Yeah. So this will be free from x. This will be a constant, the flux, when x has no power, when x is equal to, when the index of x is 0. So that is true only when m minus half is equal to 0. So that is true when m is equal to half. Yeah. So we don't really need the exact expression of Q. I was thinking you'll need that, the from the exact solution of the temperature profile or with respect to Y. That is one way of doing, the more better way of doing. But even if you don't do that, from the definition of Nusselt number also, we can arrive there. This is easier, I think. Okay. Any questions on this? Okay, so let's move along. We'll move on to question number 9, which is asking us which of the following assumptions are correct for laminar boundary layer flow over a flat plate with uniform heat flux at wall. So once again, uniform heat flux, similar to what we saw earlier. So is it option one, negligible viscous heat dissipation? Option two, no internal heat generation. And number three, incompressible flow. So there are three conditions, and combinations of them are important. So is it option A, 1 and 2? Is it option B, 2 and 3? Is it option C, 1 and 3? Or is it option D, all three of them? That is 1, 2, and 3. Okay, so quickly I've selected D, 1, 2, and 3. Let's look if it's correct. It is indeed correct. So the first one, the heat dissipation is ignored. So this heat dissipation term, capital Phi, that is the so this is the viscous dissipation term. So if there are huge, velocity gradients, then due to the friction between the layers of fluids, there is a certain heat generation within the fluid. So that heat generation term should not be there, so that our mathematical equations are easy and nice. So we have to ignore this. Then no internal heat generation is there for any causes. So this actually falls under this second category only, that there is no internal heat generation. So usually viscous heat dissipation is written separately from the heat generation term. Now this could be due to multiple reasons. This could be due to chemical reactions or something else, some other physics phenomena going on. So that also shouldn't be there, as it messes up the equations. And finally, incompressible flow is also an assumption that we start with. So in case there is a compressible flow, there are some shocks and so on. That also complicates the physics problem. And those things are all out of the scope of our syllabus for now. We will focus simply on, you know, the very basic laminar boundary layer flows. So for that, all these three assumptions have to be taken in account, and we should know what assumptions we are making, right? So in this case, all these are the correct assumptions, and the correct solution is option D, all of these. Any questions on this? Okay, so let's move along. We'll move on to the last question of today's session. This is asking us that in an experiment, the local heat transfer over a flat plate was correlated in the form of Nusselt number as expressed by the following correlation. So in the lectures, we saw how we can derive a Nusselt number with some assumptions. So that was an entirely mathematical or theoretical process. Now, this problem is telling that in an experiment it was correlated. So, what is usually done is that multiple flat plates were taken, and there was a flow set up over them, and experimental readings were made. So uh, we can imagine that there will be temperature measurements, there will be heat flux measurements, and so on. And finally, all the results, those were plotted. So let's say I was making a plot of Nusselt number into Prandtl number. So let's say I made a plot of Nusselt number into Prandtl number power 1/3. So this can be done, right? Prandtl number is just a constant that I'm multiplying. And on the x-axis, if I have Reynolds number, let's say. And these were all done on a log-log scale. So I had log Rex and log of this. And I got multiple data points because the experiments were repeated multiple times. And using a fit of this data, I get that, that the slope is 0.8. So what does this tell me? This tells me that, and there is some, abscissa over here as well. Anyway, that doesn't matter. That gives me this number, and this slope gives me the uh, power of Rex with which the rest of the things vary. So, okay, so this is not Prandtl number 1/3. This is Prandtl number to the power minus 1/3. So this is what is usually done in experiments. And this is the truth. So whatever theory we do, if it doesn't match with the experiments, it is of no value. So experimental verification is paramount, and this is how usually uh, these very important numbers are extracted from experiments. So once all this is done, so let's come back to the question. So given that, I found that the Nusselt number varies with Reynolds number in this fashion, then what we have to do is we have to determine the ratio of average convection heat transfer coefficient over the entire plate length to the local convective heat transfer coefficient at x equal to L. So let's say the if the plate was of length L, x goes from 0 to L, and I had some boundary layer over it. And given at any x, I have some h of x. What I have to do is find out the ratio of the average heat transfer coefficient, so h bar, and its ratio with the local heat transfer coefficient at L. So at x equal to L, there will be an H. So that HL. This ratio we have to find out. So how do we go about this? Pretty simple. We know the Nusselt number. So NUX is equal to some constant. I'll call that C into REX power zero point 0.8. This is important. And Prandtl number powers 1/3. So I can club this Prandtl number as well. So I'll call it C1 into REX power zero point 0.8. Uh, okay, let's do it a step later. And this NUX can be again further divided into HX by K equal to C REX power zero point 0.8 and Prandtl number power 1/3. Okay, this REX also I'll break it down. Yeah, so let's call this U infinity X over nu power zero point 0.8, right? So this finally gives me, and this is local H at X. So Hx is equal to C into K into Prandtl number powers 1/3 into more constants, that is U infinity by nu into zero point 0.8. And now I'm separating out the X. So X is zero point 0.8 minus 1. So that's minus zero point 0.2, right? I'll club all these constants again. So Hx basically becomes C2 C1 into x power minus zero point 0.2. So now what I finally need is the h bar over hl. So hl I can simply find out from here that it should be C1 into x power, or not x, L power minus 2, minus zero point 0.2. L power minus zero point 0.2. So I got the denominator. I need the numerator as well of the ratio. So h bar is basically, I have to take a integration or summation, which is integration over the entire length L. So x goes from 0 to L, hx into dx divided by 0 to L dx. This is the formula for average over uh, one dimension. If we had to integrate this over a surface, we had to integrate over x and y both. All right. So now let's do this. 0 to L, I have hx given by some C1 into x power minus zero point 0.2 dx, and in the denominator this simply becomes L. So further doing this C1 by L, I'll take all these things out, and integration of x power minus 2 is simply uh, x power minus zero point 0.2 plus 1 divided by same thing, so plus 1 minus zero point 0.2, and this goes from 0 to L. So this becomes C1 over L, and 1 minus zero point 0.2 is zero point 0.8. So I have a zero point 0.8 here in the denominator, like zero point 0.8 into L, and x power also zero point 0.8, L to 0. So that becomes L power zero point 0.8 minus 0. Yeah. So this is C1 by zero point 0.8 L power minus zero point 0.2. Okay, so this is H bar we got. Now let's compute the ratio. So this ratio is simply C1 by zero point 0.8 into L power minus zero point 0.2, and HL we had is equal to C1 L power minus zero point 0.2. So C1 L power minus zero point 0.2 L power minus zero point 0.2, all these cancel out. What I only have is 1 over zero point 0.8. This is equal to 1.125, I think. Yeah. Okay. So this should be the answer. Any questions on this? The process was clear, right? Right? How we got there? Okay. So that's all for this week. Thank you. Let's meet again next week.